Hey guys, Mr. J here, coming at you from the home studio. We're going old school today, all the way back to pre-AP when you guys had to do podcasts. But since we're not in school right now, I thought this would probably be the best way to get it to you. Today we're going to talk about covalent bonding and polarity. This is mainly a review of what we did last year when we started talking about covalent bonding in pre-AP, but it's been a year and a half since we've done that. So I want to go through some of the things on polarity, because we're going to eventually end up drawing Lewis structures of these, which we talked a little bit about last year when we did Lewis dot diagram. We just did it from elements, but this year we're going to do for molecules. So let's go ahead and get started. Okay, remember, chemical bond is just a force that holds a group of atoms together. Okay, we call them intramolecular forces. That means forces within a molecule. And basically what we see is that the bond will form if the energy aggregate, or the total of the energy, is lower than that of the separated atoms. The atoms become more stable by bonding with each other, and that's why we form these bonds. Okay, a couple key ideas. Remember, we talked about ionic bonding. And ionic bonding, electrons are transferred from one atom to another, okay, resulting in ions, and ions of opposite charge are drawn together, and that what makes our different ionic compounds. Covalent compounds, on the other hand, what we see, rather than transferring the electrons are shared by the nuclei of the different atoms, okay? And they're sharing those electrons in order that they can get a full valence shell, or 8 valence electrons. Now, covalent bonds, remember, we're talking non-metals, right-hand side of the periodic table, and they have a tendency to hold on to their valence electrons. They don't lose them like metals do. Okay, they can't give away the electrons in a bond, so they end up sharing them. Okay, even though they can't give them away, they still want this noble gas configuration. Okay, and they get this by sharing their valence electrons with other non-metals to form covalent bonds. But by sharing these electrons, each atom sees itself, let's use that term, sees itself, as having a full valence shell, and everybody's happy, and it becomes more stable. Okay. And remember, there's different types of covalent bonds that can form. If they're sharing one pair of electrons, or 2 electrons, we say it's a single covalent bond, like hydrogen gas, H2. Okay, they're sharing, both hydrogens have one atom, they share them, so this hydrogen has 2, this hydrogen has 2, it's the duet rule, not the octet rule, because it's only the s orbital for that. Okay, we can also share 2 pairs of electrons. Okay, if they're carrying 2 pairs of electrons, or 4 electrons, we call that a double bond. In the case of carbon monoxide, we see there's 4 electrons here, 4 electrons here. Everybody looks like they have 8 when we write this out. Everybody's nice and happy. And then the third type is they can share 3 pairs or 6 electrons, kind of like N2. Okay, and remember, by sharing, this N feels like it has 8 electrons, it's happy. This N feels like it has 8 electrons, it's stable, and so it forms a good bond this way. So when these nonmetals are sharing electrons, they don't always share electrons equally with each other. In fact, sometimes one hogs it more than the other. It's kind of like if your mom tells you have to share your candy bar with a sibling, right? You break off a little corner, give it to them, because now you share it, but you're going to hold on to the biggest part of it for yourself. Well, some nonmetals have a tendency to do that. Some do share equally, and when they do share those electrons equally, we say they're a non-polar covalent, meaning that the electrons are shared equally between them. Now, sometimes they don't share equal, and we call that a polar covalent. We talked about this last year. So polar covalent is an unequal sharing of electrons between the atoms. One atom tends to hog the electrons on its side more than the other. Kind of think of it as like a tug of war, right? The stronger atom is going to pull the electrons to it, leaving the other atom kind of short electrons. But overall, what we see is that they do have these molecules, polar covalent, have a overall neutral charge to them. Okay. What they end up, this unequal sharing of electron creates a partially charged side, which we call dipolar-dipole moment. So if this side is going to be the more electronegative, it has a tendency to pull the electrons here. So they hang out here, so it has a slightly negative charge. The other side here has a positive charge because its electrons have been pulled over there. Overall, though, what we see is the charge of this covalent is neutral. Remember, these charges, this positive here and this negative, are not full charges like we would think of with anions and cations. It's a partial charge. Okay, we get a separation in these charges, partial positive and partial negative side. So basically, this dipole moment is a quantitative measure of the polarity of a bond. How polar is a bond? Okay, we can define as a property of a molecule's charge distribution can be represented by a center of positive charge and a center of negative. Okay, the negative charge is due to the bigger electronegativity value pulling the electrons to the side, and the other side then doesn't have them, so it becomes slightly positive. Okay, and so what we can do is show this dipole moment to show the direction of a polar bond in a molecule. Where does that polarity lie? Okay, and we use an arrow to represent the dipole moment, and the arrow points towards the more electronegative atom. Okay, it's showing where the electronegativity is. The tail then of the arrow indicates the positive charge. So if we look at an example here, something like this, okay, here is water, H2O, okay, here is drawing in our dipole moment. The oxygen is more electronegative than the hydrogen, so the arrow points towards the more electric we get, okay, and then the end of the arrow, think of this as like a little plus, shows the more positive. So that's how we can represent a dipole moment. So how do we show this polar bond? Okay, remember, the charges aren't whole charges, they're partial. Okay, so we use a little symbol like this, means partially positive, the one that means partially negative, so we can represent them that way. So in this we see our chlorine is our more negative end, our hydrogen is our more positive end. Okay, so because the Cl is a high electronegativity value, it's pulling the electrons more towards it than hydrogen does. It overcomes hydrogen. Okay, so the electrons end up spending more time on chlorine side than hydrogen. And that's how we can represent it there. Okay, I've talked a lot about electronegativity. If you think back, electronegativity is the ability of an atom or in a molecule to attract shared electrons to itself. It's that force pulling the electrons toward it. And on the periodic table, we see electronegativity generally increases as you go across a period and decreases as you go down. If we think about this, as we go across, we're not adding any more electron shells, but we are adding more protons. So that outermost shell actually ends up shrinking, and then the electrons are closer to the protons, so there's a greater pull. As we go down a group, okay, we are adding more shells and more shells so that the electrons are getting farther away from the protons. Excuse me, and this decreases that electronegativity, okay? And it goes anywhere from about 0.7 at the low end with cesium in the lower left-hand side to 4.0 to fluorine in the upper right-hand side. Remember, our noble gases don't attract them. They're happy. They get a full shell, so they don't really have an electronegative value. So think of it this way, or we can think of it going this way if you want a one arrow, right? Small down here, large values up here. And we're going to be talking, remember, about non-metals. So we're looking at this part of it here. Okay, and so we can use these differences in electronegativity to predict bond types, okay? And the bigger the electronegativity between them, the more polar the bond is going to be. And so if the difference between them is less than 0.5, we consider it to be covalent nonpolar. If it's between 0.5 and 1.99 or less than 2, it's covalent polar. And if it's greater than 2, it's ionic. Now understand, different references will give you different values. I just looked a bunch of these up. One value said 0.2 here, other said 0.4, this 1.7. So these are rough estimates, right? It's really always, remember, easy to tell ionic because you got a metal and non-metal, okay? The idea is the greater the electronegativity difference is between non-metals, the more likely it is to be polar. And so, okay, and that's all this image is showing you there. And so, a little practice here. So if we have a sample bond, let's say sodium and chlorine, we can look at the electronegativity difference. Here's sodium at 0.9. Here's chlorine at 3. So what's our difference? 2.1. Okay, so 2.1, that's definitely in the ionic. Also, we know we have a metal and non-metal. How about chlorine, Cl2? I don't even need to look at the value, right? Difference, two of the same elements are going to have the same, so we're going to have a zero difference. Okay, and so that's going to be covalent. Okay, it's going to be nonpolar covalent. Try these last two. Pause it really quick. Try these last two on your own. All right, let's look at carbon and oxygen. Carbon is 2.5, oxygen is 3.5. We got a difference of 1. That's going to be well in that polar covalent. Carbon and hydrogen, remember hydrogen's a weird one, right? Can act as a metal and non-metal. We see 2.5 and 2.1, so we get a difference of 0.4, which puts us in non-polar covalent as well. Okay, so pretty simple. We did this last year, just wanted to remind you of it. Okay, how about this one? I'll do the first one with you. You do the second two on your own. So it says arrange the following bonds from most polar to least polar. Well, how do we tell that? Well, the greater the electronegativity difference between the atoms, the more polar the bond is. So if we look at NF here, we got 3.0 and 4.0, so we got 1 there. Oxygen, fluorine, 3.5 to 4, so 0.4. And carbon gives us a difference of 1.5. So carbon fluorine is going to be our most polar, whereas oxygen fluorine is going to be our least. Try B and C. Pause it and try those real quick. All right, let's take a look at B. Hopefully you paused and didn't cheat on me, okay? We got Si, F, CF, and then NO, okay? Looking at C there, first thing I can see, chlorine is going to be 0, so I know that's probably going to be our least polar. B, we got 2, chlorine, we got 3, so we got 1 there, and S is 0.5 and chlorine, so it's going to go B, Cl, SCl, and then ClCl. So pretty simple, nothing too difficult there. Okay, a couple concept questions for you. What's the general trend for electronegativity across rows and column on the periodic table? Okay, explain this trend. So think about this, and then come back to me once you do. So generally speaking, what we said, we see the electronegativity increases going from left side to right side across the period because the number of protons increases, which then decreases the atomic radius, which increases our effective nuclear charge of that attraction. As we go down, though, the electronegativity decreases because the size of the atom is increasing because we're adding more sublevels, right? Which then we get what's called, it's not as great due to shielding. Shielding is just the distance between the nucleus and the outermost shell there. Okay, just try another one here. If lithium and fluorine react, which one has more of an attraction for an electron? Why? So they're both, if you look at your periodic table real quick, lithium and fluorine are both in the same period, but lithium's to the left, fluorine's to the right, so we know its answer is going to be fluorine, right? Both values in the same principal energy, but fluorine has a greater number of protons, therefore a greater attraction and smaller radius. How about between fluorine and iodine? Once again, both halogens, but iodine is lower down, so fluorine's going to have a greater attraction because iodine is going to have a larger diameter, so more of that shielding effect. Pretty simple. Alright guys, that's all it is. Now, as I said, with those values for predicting electronegativity, they are, depending on what source you use, different values in it. So we're going to talk about in the next couple videos here how we can use our Lewis dot diagrams or Lewis dot structures to actually predict it if we don't have a electronegativity table in front of us. Alright guys, if you have any questions, please drop me an email. We'll talk to you soon.